Hello, good morning, young friends. Today, I will discuss the application of transition state theory. I have already discussed the derivation of activated complex theory, and as you know that there are two important formulations. One is the derivation of transition state theory using statistical thermodynamics, and you have seen that I have used two partition functions. One is vibrational partition function and another is translational partition function, and with the help of these two partition functions we are able to determine the final equation of transition state theory, which is the concentration of the activated complex. But there is a second part which is very important, that is called thermodynamic formulation of the transition state theory. And you know that you can call it that is a extension of the collision theory, and there is a relationship between collision theory and activated complex theory as well as the Arrhenius equation of effect of temperature. But today I will discuss mostly some of the application of that transition state theory. Now you all know that transition state theory is sometimes it is called absolute reaction rate theory or theory of absolute reaction rate, because sometimes we call it is a ultimate theory, and because there is a question of activated complex, so therefore we are concerned about this concentration of this activated complex. So therefore it is actually known as activated complex theory. And you all know that the final equation I have already derived, the rate constant Kc is equal to Boltzmann constant T H and equilibrium constant of the activity. I have already discussed. I will not discuss about the historical discussion on the transition state theory, because you know that basically Henry Eyring is responsible for this theory, and actually Henry Eyring discovered this theory in 1935. But before that I also told you that one René Marcelin is a French scientist. She also published a paper related to that transition state theory. So before going into details of that application of the transition state theory, I must tell you some of the important research papers, and for this particular lecture I have gone through all these research papers which are available in our library as well as the internet. You can see it, and basically you know that Eyring, and the title of the paper is the activated complex in chemical reactions. Similarly, I also told you that not only Eyring but M.G. Evans, Michael Polanyi, as well as the E. Wegener, Pelger, they also contributed, because they have also published the paper in the year of 1932 related to some speed constants and other things. And you know that M.G. Evans and Polanyi some application of the transition state theory. And if you ask me that, sir, what is the actual application of the transition state theory? So I should say that the exact calculation of thermodynamic formulation, like I will discuss the entropy of activation calculation of, then free energy of activation, then enthalpy of the activation. Then you can ask me, sir, what is the relevance of these parameters? So I must tell you that whenever we study any type of the chemical reactions, so with the help of these activation parameters, we can figure out the mechanism of any type of the reactions. So therefore I am just showing you this most important contribution. Similarly, you know that I always follow, because there are many derivations available in the books, but my dear friends, young friends, that I am using the most important research paper of Ledler. You know that I always ask my student to refer this book, Chemical Kinetics by K.J. Ledler, and it is available in our library also. And most of my derivation, because as I told you, there are different types of derivations, but today's lecture I am using the derivation from this book. And I will also show you the research paper. They have also published, and Glaston is a very well-known physical chemist, and there is a book, Physical Chemistry by Glaston. It is also available in our library. Then second, Ledler and Irene, the theory of rate processes, the kinetics of chemical reactions and other things. And you can see that is the one of the very important paper. Already it is published in 1957. The very well-known physical chemist, particularly Nobel laureate in chemical kinetics, his name is Hinshelwood. And he actually, if you go through this paper, so you can see some of the significant contribution of the chemical kinetics in the past few decades. And he is Nobel laureate in the area of chemical kinetics. And this is the one of the most important paper, and I have already in class, I have already derived you that equation. You can see this thing. Don't worry about this transmission coefficient and other things. And again you see that, again, so there is a relationship between this transition state theory and application and other things. So this is one of the formula of the famous equation, you know. But today I will not discuss these things. I will only concentrate on the application of that part. And again, this is a very important paper, Journal of Physical Chemistry, 1983, the development of the transition theory. And of course, most of the things are available in that book also. So I am just showing you that paper. Now, if you ask me, sir, what are the different applications of that transition theory? So today first I will discuss about the Irene plot. I think you may be aware of this Irene plot. It is nothing but the graphical representation of, or graphical calculation of, entropy of the activation, entropy of activation, as well as the entropy of the activation and enthalpy activation. And second is the determination of different thermodynamic parameters. And I have already discussed, one is enthalpy of activation, entropy of activation. Then suppose that we can write like that. It is actually standard. Sometimes you can write like that also. So there are so many methods is also there. You can write like that. It is standard like that. So don't worry for this. And third application is that the relationship with the Arrhenius theory. And this is a common theory. This is a common application. But bear in mind, when you perform some experiment, and determine the activation parameter. So, and suppose your reaction is unimolecular or gaseous type of the reaction. So, there is a slight modification of this theory, that equation. Similarly, for bimolecular reaction also, there is a very small changes. Apparently, you will find no difference. But if you see very carefully, so activated complex theory for unimolecular or gaseous equation is slightly different, and for bimolecular reaction also it is slightly different. Now I am coming to, first I will discuss the Eyring plot, and again yes, you are definitely referring many good books like Levine or Atkins or Glaston or Ledler, but in addition to that there are some good research papers also. You see, a common misconception about the Eyring equation, because I am just, first I will discuss the Eyring equation. So it is published also in Royal Chemical Society Journal, New Journal of Chemistry. So don't worry about this Eyring equation. I will explain very simple. It is a graphical representation, and by that graphical representation we can calculate the entropy of activation as well as the enthalpy of activation. So I will explain these things. So let me start with the derivation. So let me start with the very simple derivation. First is the Eyring plot. Okay, my first point. So for Eyring plot, I can start with our normal equation. In order to differentiate between the rate constant and Boltzmann constant, I am using subscript Kc, means it is rate constant. Okay, and this is Boltzmann constant, T, this is Planck constant, and K. That is our main equation. And we have already seen that, because here I am using like that. I have already derived these things, absolutely. And using the Gibbs-Helmholtz equation, I will not discuss the Gibbs-Helmholtz equation, everything, because I have already derived that. My concentration is that what is Eyring plot, and so you know that I can write like that, Kc. It is very simple. KBT H. Now you know that delta H minus T delta S. So if I substitute these things, so minus delta H RT R. Okay. So now what is Eyring plot? Sometimes this equation is called Wien-Jones and Eyring equation. Sometimes it is called Wien-Jones and Eyring equation. Eyring. So it is called Eyring equation. But I am interested in the Eyring plot. So if I just slightly replace this equation, should I write like that? Kc H Very simple. KBT, you see, is equal to exponential. You can standard, you can write like that or whatever you want. Now taking logarithm. Taking logarithm. So I can write like that, natural log of rate constant, whatever it is, Planck constant, KBT, bracket you can write like that, very simple, minus delta H. If time permits, I will give some numerical problem, RT, plus delta S by R. This is called Eyring equation. Nothing, just I replace this thing. Now what is Eyring plot? Means experimental. Suppose I am giving you a simple example, any type of the reactions, and you perform that chemical reaction different temperature. Okay. So naturally, suppose you are using 4 temperature, you will get 4 values of rate constant. But Planck constant is constant, Kb is constant, temperature different. So if I plot a graph, you see this is Eyring plot. This is the first application of transition state theory. If I plot a graph between, if I use now yellow color, same thing, natural log of. In some books, what I have seen that they have only plot between Kc and T, like you can Kc divided by H, Kch upon T, or simply Kc divided by T. Kc divided, you can like that also, Kc divided by T. But I am using the book of chemical kinetics and ladies original research paper. So they have seen this Kc, H and KBT, and 1 by T, you see, 1 by T, 1 by T, just like your Arrhenius plot like that. And suppose you are using 4, so 1, 2, 3, 4, like suppose. So I am getting 4 values. Similarly, state line equation, y is equal to mx plus c, like that. So gradient or slope, slope or gradient, whatever I am talking, will be minus delta H divided by R, and the intercept is the delta S by R. Now suppose if you just write log base 10, so you know delta is divided by 2.303 R, delta is by 2.303 R. So this is called the Eyring plot. There is a possibility of numerical problems or some other type of question or objective type of the question. You can see it there sometimes, if some focus is required or not, it is automatically, so you can see it there also. So it is clear what is Eyring plot. Eyring plot is a graphical representation, and for that we need only the values of different rate constant and different temperature. So we will take a plot, and from that plot we can determine the delta H as well as the delta S, that is called the standard entropy of the activation. So it is quite natural that if it is negative, so we will get the values of. So if time permits or in homework, you can perform such type of plot. So say for example K25, K35, K45, K65. So this is the first application of the, sometimes it is called, this equation is called Wien-Jones and Eyring equation, but major contribution is from Henry Eyring. So therefore it is called Eyring plot, or sometimes it is called the Eyring equation. Okay. Now I am coming to the second part, the thermodynamic derivation of by other methods, because when you perform some of the experiment in your class, practical classes, so you will get, or you will determine the energy of activation, isn't it? You will determine the energy of activation. So our second objective is that replacement of that delta H, because in my last class I think I had given you a problem, 2 rate constant, 2 temperature, and I asked you calculation of the log A as well as the energy of activation. So if you know the energy of activation, so my second question is that suppose you determine the energy of activation, maybe it is 54 kilojoule or whatever it is. So how do you calculate the entropy of activation? Okay, so that is the last or second application. It is very simple. So I am coming to that second part. Okay. Second part is application number 2, the last application. The determination of delta G, delta H and delta S. And again it is of 2 types of things. One is for unimolecular, small difference. Second is bimolecular. When you do research, you should be very careful. Bimolecular. So let me start with this thing. We know that Kc is equal to Kb, again same equation. Okay. This is one form of the activated complex theory. So if I taking simple logarithm, natural log of Kc, rate constant, is equal to natural log of Kb H plus natural log of T, absolute P, plus natural log of C. Very simple. So I am just solving the thermodynamic formulation of transition state theory for unimolecular reaction as well as for the bimolecular reaction. So if I take the derivative from a differential form, so I can write like that: natural log of Kc Then because it is a constant, Boltzmann constant and the Planck constant, so I can simply write 1 by T, and it is so you are all aware of these things. That now just remember your Arrhenius equation, and this part can be written as energy of activation T square. Similarly, this part you all know that very important one top reaction. So what I can write 1 by T, then delta E. It is called internal energy, or you can write in some books it is written like that, but it is here I am using delta E by RT square. Now if I take LCM, simply it is RT square, this of course EA RT square. So it is RT plus delta. So what I can write? I can write finally EA RT or delta E by RT. Why I am doing such type of exercise? Because when you perform the experiment and suppose you are getting two values K1 and K2, suppose it is in 27 degrees centigrade, this is 37 degrees centigrade. So suppose 2 to 10 to the power minus 4 or 3, whatever it is, minute inverse 1, 4 into 10 to the power minus 3, minute inverse 1. And you can easily calculate the energy of activation. But my question was that how do you calculate entropy of activation with the help of transition state theory or Wien-Jones and Eyring equation? Because if you see that equation, you will get the delta H, enthalpy of activation. So I have to remove that delta H from that equation for the calculation of delta S. Okay, so therefore I am doing all such type of the experiment. So let me now I have only one equation. This. Okay. Now we know that our Wien-Jones and Eyring equation is equal to Kc, Boltzmann constant, T, H, you know, minus delta H, exponential of course, RT, R. So I have to replace that delta H. Okay. Now again, as I told first part, there are two type of thing. One is called unimolecular. Sometimes it is for solution and like that. Another is the bimolecular. Bimolecular. gaseous reaction and other things. Now, if you ask me, sir, what is the difference between that EA and relationship between delta H and RT? So, if I plot one energy diagram, let me solve first unimolecular, then I will talk about the energy diagram. So, now if it is a unimolecular reaction, we know that in thermodynamics there is a important relation of enthalpy internal energy relations. You all know this is a very simple equation. And I can write like that: delta H is equal to delta E P delta V, change in volume. And of course, as we are talking about the activated complex, so always I put this sign. So, as because it is unimolecular type of the reaction, we know that for gaseous system we can write PV is equal to RT. You all know these things: P delta V delta N RT. Number of moles is changed, you can write that. So for unimolecular reaction, basically it is zero. There is no change in volume. So I can write that whatever the value of delta H, enthalpy of activation and internal energy is same. So I can write like that: EA is equal to RT plus delta H. Because again, bear in mind, I am talking about the unimolecular reaction. So therefore, delta H is equal to EA minus RT. Very simple. So now you substitute the value of here from here. So what I am getting now for unimolecular reactions. So it is KBT H. Now here we can write exponential minus. So it is very easy, it is replaced, and this RT exponential, because it is minus, so RT by RT, and same thing. So you can write this again. So I can write for unimolecular E KBT H, exactly same. Now you can calculate the entropy of activation using the Eyring plot also, because if you perform some experiment K1 and K2, and you can very easily calculate the energy of activation like that. So you can calculate the delta S. Now I will proceed for the last part, this is the bimolecular reactions. Now before that, as I told you that if you want to know the difference between the normal activation energy and the concept of the quantum mechanical concept or the classical concept, so you can plot a graph. And I can use this part, and it is available in the book of Ladler. So if I just, you know that it is activated part is like that. So you know that this is reactant, and it is product, and it is activated complex. Everywhere there is a 0 point energy, you know, or 0 point energy level. So here for reactant it is, if I write like that, it is 0 point energy level. For activated complex, the 0 point energy level is this, and it is normal, right? And here I can write the energy of this colliding activated complex or particle complex. So basically, the difference between the 0-point energy level of the activated complex and 0-point energy level of the reactant, so this is actually, I can call it the energy of activation of the quantum mechanical, because whenever you are talking about the 0-point energy level, it's related to the quantum chemistry, quantum mechanics. Whereas, if I consider it is normal energy of activation from this to this, these things, normal. You can call sometimes classical things of these things. But now the question is that what is the difference between this delta E and delta H, and what is the role of the RT? So in order to understand the difference between these two things, so there are two things, maybe here the average energy of reactant, average energy of the colliding molecules, like that. Here is also this thing. So that is the thing. Sometimes average molecules to here is complete EA, and average molecules of that colliding molecules and difference between, you can call it is a delta H and delta R. So by that graph, that Henry Eyring tried to solve the difference between this EA, RT and delta H. But ultimately, when we promoted into the second semester, there is a very important theory. This is called RRKM theory. When you understand the RRKM theory, then it will be very easy for us to clear-cut distinction between the internal motion and the actual vibrational energy and translational energy and other things. So that is RRKM theory. So I will not discuss. Now the last part, now I will proceed for the bimolecular reactions. Now, suppose it is a bimolecular type of the reactions. So let me also I remove this part. If it is a bimolecular type of the reaction, so I can write delta H is equal to delta E, P delta V, RT, or you can write RT delta N or delta N RT. Again, it is for bimolecular reaction, that is A plus B is equal to this single entity of the activated complex, and then of course the product, like this. So you can very easily calculate number of moles of the product is 1, because it is a transition state, and number of moles of the reactant A 2. So delta N is equal to minus 1. So I can write delta E minus RT. So delta E is equal to delta H plus RT. So if I write the value of delta E is equal to, I have to replace the, where is our final equation? E by RT. So delta H is, I have to replace, delta H is equal to delta E by RT, and delta E is equal to delta H plus RT. Just a minute. Delta H is equal to delta E, H is equal to E plus dV, no problem. So delta H is equal to delta E minus RT. So I have to write, what is our first equation? delta is delta E value. So delta is equal to E plus RT. Just a minute. So first I just H and EP, no problem, delta E, RT delta N, because I have to replace the delta H. So RT, so I can write, simply I can write delta E minus RT. Now where is our first? EA, will have written this thing. What I am getting? RT plus delta E. So first I have to write the value of delta E here. So it is very simple. EA is equal to RT plus RT plus del H. So what I can write directly in place of RT plus RT, 2RT. So simply delta H EA minus 2RT. Directly you can write like this. And now we substitute the value. Let me rub the first the unimolecular thing. So I must remove all these things. So in place of delta H, I can write here minus, let me write in white color, minus EA minus 2RT. So exactly same, just a slight difference. KBT H E minus A by RT. Then again minus plus 2RT, this cancel, delta S R. So for unimolecular there is only one E value, and for bimolecular Kc you can write. So it is a very, as I told you in my first part, there is a very minute change. KBT H initial E by RT delta S, and you can start like that. Star you can write delta S by R. So for gaseous reaction also you can use this type of reaction modified from the Wien-Jones and I. Now the last part, that is the relationship between Arrhenius equation and the transition state theory. That is the last part. So that you can very easily calculate with the values of the rate constant of one particular temperature and rate constant for the another temperature. So let me just 2 minutes without considering the unimolecular, or so I am just using this general equation. So KBT means here minus RT taking logarithm natural log KBT H minus A by RT plus delta S. Or what I can write? Natural log of Kc minus plus A by RT. You can write it bracket also, equal to natural log KBT plus. What is the relationship? You know that Arrhenius equation again. That means if you know the value of frequency factor, you can easily calculate the delta S. Yesterday I had given a numerical problem also. I do not know whether you solve it or not. Minus A by RT. It's very simple, undergraduate level thing. So if I can write log of K plus A by RT is equal to natural log of A. Okay. So you just substitute these things. So last equation is that. Here I can write natural log of A. Yes, minus natural log of KBT H, like that, is equal to delta S by R. So by that method, you can calculate the delta S. If I just convert it into log form, so it is 2.303 R. R may be 1.9187 calorie per degree per mole, or even you can use the SI unit, is equal to log of A minus log of K, Boltzmann constant, and absolute temperature H. So let me summarize today what I have discussed with you, that the application of transition state theory or absolute reaction rate theory. First application is that with the help of Eyring plot, one can determine the most important parameter, that is called the entropy of activation. And as I told you that because in our research laboratory we have performed large number of simple hydrolysis reactions. Some reactions are unimolecular, some reactions are bimolecular. What we have observed that means if the values of, suppose yesterday also I discussed that log of A is suppose very high, 25, and that part is 20. So it is a positive value. The delta entropy of activation is a positive value. So this indicates it is a unimolecular type of the reaction. But suppose this is 20 and this is 25. So it is a minus. Entropy of activation will be minus. So according to my observation, if my reaction follows unimolecular reaction, so I will get the positive value entropy, and if my reaction is, most of the reaction is bimolecular type of the reaction, so I am getting the large negative entropy of activation. What does it indicate? That this is the significance of all these thermodynamic parameters. That means from these values of delta G activation, delta H and delta S, one can figure out the reaction mechanism. And this is the example of Arrhenius correlation between. And similarly, there is a correlation between the collision theory and transition state theory. In my next class, I will discuss this theory. Just show the student. So I think you have understand the application of the transition state theory. Thank you very much. Thank you.